稍等2分钟。
这节课还是有那个唐景居老师讲说那个 p-adic 表示，约化学中的那个 p-adic 表示，大家欢迎。
So we look at representations. Of a p-adic reductive group. So here F now is assumed to be QP. And G is a reductive group. So because I will not use the algebraic group G anymore. So this G is reserved to be the fixed point of the algebraic group. Okay, so G is the any elements in G has entries in F, and IV is a representation of G. Okay, so that means pi is a group homomorphism from G to the endomorphism of V that is invertible. So V is assumed to be a complex vector space. Okay, so for convenience, I take the field, the base field of V to be the field of complex numbers. Okay, so this is the classical definition. Because G has topology, so I need this map to be continuous. Okay. Then several definitions. So we say we call pi irreducible if there is no proper non-zero G sub-representation in V. Okay, so you cannot find a smaller non-zero representations in V. So this is just parallel to the usual definition. Okay, now so here I want to define two notions that is similar to the case for real groups. Okay, so if G is a real group, then we can take derivative. But G is now a group defined over QP, and QP is a totally disconnected group, totally disconnected field. So we cannot take derivative. But still, I want to define something called smooth. Okay, so what's the definition? So we call pi smooth if for any vector V in my representation space, there exists an open subgroup K such that this K, any element inside K fixes this V. Okay, so that means pi K, if you operate on V, is just equal to V. Okay, for any K in K. And so this is just like how you define smoothness for the GK module. Okay, and here's one more definition admissible that is also parallel to the admissibility for GK modules. for real groups. So we call pi admissible. Okay, call pi admissible if for any open subgroup K. So for any compact subgroup, the dimension of the K fixed points of V. Okay, this is a subspace. So you can check its dimension is finite. So by the way, this group G is infinite. So in general, an irreducible representation of G is usually infinite dimensional. Okay, so it's quite different from finite groups, where any irreducible representations are finite dimensional. And you will expect all the theory you learn from finite groups like character theory or what else? Orthogonality relation, Fourier transform, other things you can do for representation for finite groups. They all become very complicated for this p-adic group. Okay. So I will not go into very deep theory, but I just give you some basic constructions. Okay. And you'll see already for infinite groups, things are getting very complicated. So let me give some examples. Say this simple example. This is actually way too simple for a single example. So this, say I take G to be GR like that. You just take the determinant. So it depends on F cross. And if you take the norm, okay, so away from the 0 point, the norm is group homomorphism to C cross. So it's a one-dimensional representation. For the general linear group. Okay, so this is one example, but because this is an infinite group, usually an irreducible representation for G is infinite dimensions. Okay. So I'll try to reach some example towards the end of the course, but so far this is the only single example we have. Okay. By the way, and you can check this is smooth and admissible. Okay, so I leave you to check. And before I move on, just a remark. So here you see I take all these K to be open subgroups in the definitions, but actually for well, maybe let me. So in the definition of smoothness just very smooth and admissible. Okay. In these two definitions, we can replace the word open by compact open. Okay. I leave it as an exercise for you. Maybe I should really write this is an exercise and check. If I replace this word open by compact open, we get an equivalent definition. And the same for here. Also, this admissibility let's see, how should I say it? Maybe I say it this way. Okay, so here's another equivalent definition for admissibility. Which is similar to what Tenfang Yang gave in his lecture for real groups. So here I take any compact open subgroup K, and I take any finite dimensional representation. I also need this to be irreducible. Maybe not, but well, we can assume it anyway. Okay. Okay. The point is this has to be finite dimensional. If the isotypic part of V, okay, the lambda isotypic part, okay, this is the lambda isotypic part of V is I put it this way, okay? V lambda is the isotypic part of V, then pi is admissible if and only if the dimension of pi V lambda is finite for any k and any lambda and irreducible representation. Okay. So this is another equivalent definition. Okay. This V is just pi. Okay. So V is just the representation space of pi. Okay. Basically, you can view these as the same thing. Is it okay here?
What is non-isotypic part?
Isotypic part. Okay. So this word isotypic means maybe I write it here. Okay. This V lambda is equal to the sum of all K subrepresentation of V. Okay, so V is a representation of G, but you can restrict it to K. Okay, K is a subgroup of G. You restrict to K, and then you just take out the lambda part. Okay, that means you just extract all these subrepresentations that are isomorphic to lambda. Okay, the sum of all subrepresentations that are isomorphic to lambda. Okay. Any other question? So these are some simple exercise. So maybe, by the way, I should give you some maybe some ideas. Okay. So the essential idea for all these is that, say, if you take two compact open subgroups, okay, say K0 containing K1, they are compact open subgroups. Then the index is finite. Okay, so this is again a simple exercise in it's actually about topology. Okay, basically because this is open, this is compact. So if you take quotient of K0 by K1, because K1 is open, then you get a discrete group. And a compact and discrete group is finite. Okay, so that's the reason. Okay, so here I want to define a special operator, which will be used very often. So first of all, I need to take a harm measure. So by the way, this G is reductive. So a reductive group is unimodular. Okay, this is a known fact. And by unimodular, it means i.e. G, this group is G, so G has a left and right harm measure. Okay, I use the symbol DG. Okay, by harm measure, it means it's left and right invariant. There are, of course, groups that are non-unimodular, so I'll talk about this later. But for a reductive group G, that is okay. And with this measure, I define this projection map. Okay, say here this K is any compact open subgroup. So I define this operator pk on V. Okay, so I input a vector V. This is just average over K under the group action. Okay, under the representation. So you let pi K acting on V, and you average over K. and the measure is taken to the EG. Maybe I write it as G. Okay, this little k is G. Okay, so I get a parallel notation, and G is in K. So just take average, but I still need to divide the volume of K. So the volume of K with respect to this measure. And this is positive because K is open. Okay? So it has a positive volume. And you can check because of this averaging, this is just a projection operator from V to the K fixed point of V. Okay? So this is a projection operator. So this kind of construction is very basic in representation theory. Is that okay for this definition? So usually I can see Zhifeng Peng nod his head, but any students have questions? No? You familiar with a projection operator?
What is the definition of reductive groups for the group defined over QP?
Defined over QP.
And how to define the reductive?
Oh, reductive just means okay. First of all, it's independent of the field. It doesn't matter. I mean, this notion is a reductive group. This notion is independent of the base field you define. It's a geometric notion. So the definition is unipotent radical is trivial. Okay. But you can define it for any field. Okay. I think this technique, this averaging technique is should be familiar in the theory of finite groups. Okay. So I'll continue. By the way, so after all these definitions, I should say for today I'll talk about contragradient representation. Contragradient. Yeah. And induced representation. So that's the plan for today. So, okay, I'll continue. From now on, I'll just assume every representation is smooth. Okay, so let I be a smooth representation. And I define this contragradient Well, this word is a bit complicated. So a more intuitive word for this is the smooth dual of the representation pi v. Now, as a space, what is this? So in simple, it's v tilde. Okay. As a vector space, it's just all the linear functional of v. So all the linear homomorphism from v to c, such that now I want to impose a smooth condition on these linear functional. So that means for each of these f, there exists a compact open subgroup. I just write compact open. Okay, K. For each f, okay, for each f you can define, you can find such an open compact subgroup K such that if you let f acting on pi k of v is equal to fv, okay, for every v in v and k in k. Basically, that means if you view k acting on f in this way, then k fixes f. So it's just parallel to the smoothness condition for v, but now it's on the dual side. Okay, smoothness condition on the dual side. Okay, if you check the smoothness definition, then you can see this is just parallel to what I defined it before. And by the way, so this is just the space, the action. Okay, so pi tilde of g on a linear functional f. Okay, so this is the representation. So pi tilde. Okay, you put a group element and you let it acting on f. So what is the action? Now this is another linear functional, so I can put v, and the value is just how you act on functions. Okay, so you have to take inverse for g. Then with this construction, the representation, can you see that? There's pi tilde and v tilde. So that pi tilde, v tilde is a smooth representation of G. So given one representation, I have another one.
On the right hand side, the pi tilde is pi on the right hand side.
Yes, sorry. Yeah, this is pi. Yeah, thank you. So this is pi. Okay. And now remember we also defined it admissible representations. And here you can check admissibility behaves well under taking contragradient. Okay. What's the meaning for that? So the meaning is in this preposition. Okay, the following are equivalent. You know this shorthand notation. Maybe I write it once and. Okay. So TFAE stands for the following are equivalent. So there are a couple statements. A is that pi is admissible. B is this pi tilde is also admissible. C is pi double dual, which is by definition the smooth dual of the smooth dual of pi. It is isomorphic to pi as a G representation. Here I won't go to the proof, but let me just say you can check it as an exercise. Remember for admissibility, we have to check this VK, whether it is finite dimensional. But now to check the admissibility for the dual, we now have to check the K invariant space for V dual. Then you check this is just isomorphic. Yes? This is just isomorphic to the dual space of VK. And here I'm not assuming this VK to be finite dimensional. Okay? You check this first. And basically, this one implies the equivalence of A and B. And for C, you just do more work, okay? Take the double dual. Okay, so before I go to the topic of induced representation, let me see if you have any question. Okay, so now I talk about induced representation. Are you familiar with the definition of induced representation in the finite group case? You remember the definition? If I have a subgroup, I want to construct a representation of the larger group starting from a representation of the smaller group. Okay, I'll review that in a moment. So, but first of all, I want to look at the subgroup itself. Okay, so let H be a subgroup of G. Now here I don't assume H to be reductive. H is not necessarily reductive. That means it's not necessarily unimodular. Okay. H may not be unimodular. That means its left half measure may not be equal to the right half measure. These two are not, may not be. Thank you. It's better to assume it is closed. Okay, so these two may not be equal. That means there's a character, let me see, is on this side. That measures the difference between the two measures. So there exists a character. A character means a one-dimensional representation. Okay, like this. Okay, such that it measures the difference. Say for example, if this H is the Borel subgroup B, then you can check the left half measure is different from the right one. So you check, you compute this modular character. Okay, this is called modular character. And it's a non-trivial character if H is the Borel subgroup. Actually, any parabolic subgroup is also true. Okay, you get a non-trivial character. Is defined up to a scalar. No, I need it to be a character, right? Well, I think the measures are defined up to a scalar. Let me see. I think you can scale it so that you get a character. What is a character? What is a character? It's a one-dimensional representation.
Oh.
Or some people call it a quasi-character, right? Yeah, character, maybe character means something lies on the unit circle. Okay. If you want, you call it quasi-character. But usually, if you look at some modern papers, they just call it character. Now, yes, any question? No? So I define induction, okay? So if I have a representation for H, okay, so that, U. Let it be a smooth representation of H. And I define this induced representation of sigma. So if you recall the usual definition, so it contains functions from G to this vector space U. That the usual definition tells you that if you have any H translate of your function, this is equal to, okay, so here we have Fg. Remember, it's a function from G to U. So this is a vector in U. In particular, you can add this vector by an element in the group H. So we take H out and add on Fg by sigma. Okay. So for finite group, this is the definition for induced representation. But now, because we have a smooth representation for p-adic groups, make a smoothness condition. So there's an open, compact open subgroup K, again depending on your element F, such that is on the right. So it looks like this thing. And the region preserves your function F. For NG. In G, and this is little k, so okay, for in K. Okay. So two conditions. And I also need to define the following. Compact induction. In symbol, this is C, IND. So just add a C in front of the induced representation. So by definition, it's again some functions satisfying these conditions, but now an extra condition. F to be compactly supported modulo H on G. Okay, that means okay. Maybe I write it here. That means away from compact set of G mod H. Literally it means F vanishes away from a compact subset mod H of G. So that means there exists a compact subgroup, because I don't want to confuse with this given K here, so maybe I write it as J. Okay, there's a compact. There's a subset J in G such that if you project J on to G mod H, so like this, such that this subset is compact in G mod H, and F vanishes away from J. Okay, a little bit technical here. But this is this technical condition. Yes.
Should they be open compact or just?
I think it's just compact.
But if compact is not a neighborhood of.
It doesn't matter. Maybe it's equivalent to compact open. I don't know. But from the definition, from the word, I think you don't need this to be open. Yeah, if it is not open, then as a closed subset, that is even much better, right? A closed subset is even smaller than an open subset, so that will be even much better. It doesn't matter, I think, as long as this J is compact modulo H. Okay, I'll just give a proposition that originally I want to talk about the proof, but I think I don't have time. Proposition. Okay, everything is just like what I've defined it. Then I look at the compact induced representation, and I want to compute the smooth dual. This is isomorphic to the usual smooth induction, not of sigma, but you multiply this modular character to it and take induction. Then it is isomorphic to the contragradient of the compact induction. Okay. So I don't have time to go through the proof. So that's why I need to talk about this modular character, because this little devil always appear if you do this kind of basic construction. In the case when H is not a reductive group. So it's a little bit asymmetric here. So to get a better expression, we define this. So we denote. Okay, so this symbol is iota. It is the Greek letter for I. H. Sorry. Iota from H to G of sigma is a twisted induction. So it's from H to G of sigma times the half power of this modular character. By the way, this modular character is unramified. I haven't defined this notion yet, but the point is that I can take half power for this character. Okay? And if I do this, then you can check. The compact twisted induction from H to G of sigma, I think the dual is isomorphic to the twisted induction of sigma. Okay, so you get a better expression for this statement. Okay. Here this delta H is gone. Okay. Well, not gone, but actually hidden in this definition.
Why is it not sigma contributing?
Y is not thank you. Yeah, sorry about that. Okay. So this looks better. Now,
Is this compact delta defined by the compactor inductor?
yeah. Okay. And finally, I still have a few minutes, then I'll talk about parabolic induction. So it's just specifying H to be a parabolic subgroup, okay, in this case. Take H to be a parabolic subgroup P. And now here's a little caution here. For parabolic induction, I take a smooth representation sigma U of M, not P. Okay, so this M is the Levy component of P. Okay, remember P can be decomposed into M times N. Okay, so I take a smooth representation of M, but extend it to P trivially on N. means I want to define sigma on P. So P contains element which is a product of element in M and an element in N. And by definition, it's just sigma M. Okay. The reason is because I don't want a representation on a non-reductive group. Okay, I want to start from a representation on a reductive group. Okay, M is reductive, P is not. And the parabolic induction is just iota from P to G, okay, of sigma. And notice that this is the same as the compact induction. Well, the essential reason is because, remember, I gave this characterization. For a parabolic subgroup, its quotient by G is compact. Okay. So if you check the definition, the compact induction, okay, that condition 3 here, is always satisfied for any f, okay? because this G mod P is compact. Okay. So I don't have to care compactness or not for induction. Then I just give 2 propositions, then and also 1 correction. Okay, then I'll stop here. So 2 propositions is just the admissibility. Okay, so if sigma is admissible, then the parabolic induction is also admissible. Another fact is about whether sigma is a unitary representation. So maybe I recall, okay, recall sigma is unitarizable. If there exists non-degenerate Hermitian form on B, because sigma here I use U for the space, so U. So if there exists such a Hermitian form on U, which is sigma invariant. Okay, that means if you let sigma G acting on both entries, where U and U prime is in your vector space U. Okay, if you let any G acting on this, let me say this is a representation for H. For any G in H, if this pairing is equal to the pairing without G action, okay? So if this relation holds for any U and U prime, then is sigma invariant. And if such a Hermitian form exists, then is unitarizable. So I think you have already learned this in the finite group case, because any finite dimensional representation of a finite group is unitarizable. You just define any Hermitian form on U, that is okay. And if it is not invariant Hermitian form, you just take the average of that. Okay. But because now G is a p-adic group, usually you cannot take average to a Hermitian form that is not invariant. Okay? So the technique fails for p-adic groups. So some representations are unitarizable, some are not. But if sigma is really unitarizable, then this inductive representation is also unitarizable. By the way, so there are a lot of representations that are not unitarizable. Say if you take a member of the general linear group, I take the dependent and the norm of that. But I can still take a power on the multiplicative subgroup of C. Okay, that means if I have a group element G, I take it to be the dependent of G, and take the norm of that and raise it to the power S. Then this is unitarizable if this character, say I use the symbol nu s, then nu s is unitarizable if s lies on the unit circle. Unit circle. Sorry,
You mean the imaginary line?
Yes?
You mean the imaginary line?
Yes, sorry, yeah. Sorry. Yeah, because this is in the power. Okay, sorry. It's unitarizable. If real part of S is 0. Yeah, sorry about that. Yeah, so that the image is in the unit circle. Okay, that's what I mean. Okay, finally, just a small correction. When I define admissibility, I say this dimension of Vk is finite. But a priori, I should say pi is also smooth. I think I forgot to mention this. Okay. First of all, pi has to be smooth, and for any compact open K, the K invariant subspace of V is finite dimensional. Okay, so two conditions. Okay, so smoothness is important. So in the definition of admissibility, you add this smoothness condition. Okay, so that's it for today. Any question? Is you? This sigma is a representation from H on the vector space U. Okay, so this is the underlying vector space for sigma. Perhaps write it in this way.